New or I don't know if they're new, but
Neutron.
neutron EDM results from a theta term using one particular formulation of lattice QCD, which are overlap fermions. Thanks.
Okay, thank you for having me here and then talk to all the experts. To compensate for the time lost setting up, but I'll keep my talk short. I'll talk about, of course, some discussing the topological charge and justify why do we use a particular type of fermions, which is chiral symmetry. And I'll spend more time discussing a particular error reduction method called the cluster decomposition error reduction. That's going to be helpful for the large volume studies of light quark masses. Okay, I'll skip all the introductions since we are probably saturated with all these things here. As of course, Andrea mentioned that there's only one dimension 4 operator here. So that's what we'll be concentrating on. Once you go to chromoelectric and other things, you have other operators which will mix and which is very complicated. I won't be touching on that, and there are other people talking about this. So one thing that sets the new calculation for the neutron electric dipole moment is this work by Brisky and so on. The thing is that when you make the matrix element calculation with the city violating vector currents inside the background with the theta term or city violating operators, one needs to really define the quark propagator or the nucleon propagator in the background of the fields, so that there's a city violating angle alpha that one needs to take into account. When that is taken into account, you can look at the F3 structure functions with this theta, then this F3, the old one, is modified. And with the new one, which is F3 prime, the old one that people calculated, and plus another 2 alpha 1 times F2. Okay. And it turns out these two terms will cancel to a large extent, leading to a very small value. For example, these are the previous results calculations of the F3. But then if you make the corrections, then the results here are about within 1 sigma in this calculation. Right? So that's a challenge. Turns out it will be very small, especially as I've mentioned, when the pile mass gets smaller, it will be, the value will be small. We know that at the chiral limit, that theta term contribution will be 0. So therefore, closer to the physical pile mass is tiny. Now, let me just refresh your memory what things have stand. Things may be updated. This is a little, could be outdated in some way. Of course, the best work here is still Andrea's work, where you have a 2 sigma results for the neutron electric dipole moment. The other ones, for example, basically do not see a signal. You can see the neutron is, the error bar is larger than the other one. Their newer results are like that. So there's no signal. And the other calculations from the energy shifts in background electric fields, you can see that the error bar is very large. And there's some results from chromoelectric and Weinberg terms, which I'm not going to mention much. Okay, let's start with the fermion formulation. We choose overlap fermion. The overlap fermion has the following properties. It has a, for example, we don't have a laser pointer. Well, here. Okay. Yeah. Okay. Got it. So the overlap operator has the following structure. It's 1 plus gamma 5 HW, which is a Hermitian, say Wilson type of fermions, and but it has a square root of this operator. So it's basically it's a matrix, so-called matrix sign function. The eigenvalues will be 1 plus minus gamma 5. Therefore, it's exactly chiral, or for the massless case. And furthermore, it satisfies the chiral symmetry has been shown. It satisfies this so-called Ginsburg-Wilson relation, which is the extension of the chiral symmetry on a finite lattice with the lattice spacing A. When you take the gamma 5 and the D operator, that is AD overlap gamma 5D, okay, additional operator. When the lattice spacing goes to 0, of course, then you go back to the continuum. But even at finite A, you have exact chiral symmetry in the following sense. And this is overlap symmetry, the only solution that we know that satisfies this Ginsburg-Wilson relation exactly. So when you look at this, you can construct a DC. The D overlap divided by 1 minus half D overlap. In that case, the DC anti-commutes with the gamma 5 exactly. But this DC is you can see, 1 over that is a is non-local, right? So this thing, you cannot directly construct that, then we don't need it. The fact is that when you look at the effect, we're always dealing with this of a propagator. The effective propagator, when you take that into account, this one has the following form. You have a chirally invariant, the chiral fermion operator plus M, which is additive. This is exactly the same as in the continuum theory. And you can see that all the chiral current algebra relations can be satisfied with this current overlap operator on the finite lattice. Okay. In particular, the topology, a T-Singer theorem, is satisfied. The topological charge is negative. You have 0 moles. When we calculate this, we do have exact 0 moles on this configurations, which we calculate, which turns out to be the same thing as trace of gamma 5 and D overlap. Okay, and for a smooth gauge field. And there's also a local definition, local charge definition, which is 1/2 trace gamma 5 D overlap, the diagonal piece. This D overlap is usually a matrix, it's XY, but the diagonal ones will give you the local. Okay, so it's all these nice features. Furthermore, it's known that it has exact anomalous word identity as shown by Peter Hassenfratz. That you can construct a singlet axial vector current which satisfies this exactly. This is pseudoscalar, which is easy to construct, and this is the local topological charge. You can show that this configuration by configuration is satisfied, which we have shown that. It's a little complicated to construct this one, but you do have exact anomalous word identity. Turns out this is essential to solving the quark spin crisis. Remember the quark spin crisis, people were arguing whether using this anomalous word identity, whether the topological charge term is part of the axial vector current or not. Well, it's part of it, but it's really from the glue mixing into the quark spin matrix element. Therefore, that's why the quark spin calculation, as people calculate axial vector current, is small. Turn out it's not. The one that contributes this really is exactly the same as from the disconnected insertions, which has a triangle anomaly predictably. So this term, when you calculate this is just exactly the same. When you calculate the say a quark spin contributions coming from the disconnected insertions, which you can verify only with overlap fermions. Of course, another feature which will take advantage of is that because of the exact chiral symmetry, the electric dipole moment is 0 when the mass goes to 0. This is a feature that Andrea has been emphasizing, and we'll be taking full advantage of that in the sort of extrapolation or interpolation in this case. All right, the first one, of course, as everybody else, we'll just test the topological charges to see how things go. This is, of course, using Wilson flow to take our configuration. Our configuration is from RBC, which uses domain wall fermions, which is it's chiral, but not as close to chiral as overlap. It's very close. It has a slight sort of residual quark mass, but that's a very minor thing. But you can see here when you do the flow here, that as I'll mention later, this seems to be a little bit of a drift, even though it's very constant. The drift is very tiny. We'll mention on that. And of course, for the overlap, it's just a constant. So we're not flowing it. I just plotted here as the number. And of course, what we did in our practical calculations, especially we need a local operator to do take advantage of the property of noise reduction. And people try to weight it with a total topological charge, and that doesn't work. It's very, very noisy because you have each configuration, you calculate vector current, 3-point function, you weigh what the topological charge, it can be 25, this configuration, another minus 25, another configuration, you need a huge of them to pin down the statistics. It's better to look at the local topological charge and see what the overlap with the vector current. So, however, at that time, when we looked at the distribution of the topological charge are not the same for different regulators, which is normal, which is not anything special. Topological charge, we know, depends on the regulators. We either use overlap or gradient flow. They don't have exactly the same, given a finite lattice configurations, but doesn't seem to change much of the physics. When you look at topological susceptibility, they seem to be the same. That was the earlier conclusion that we had earlier.
What's on the x-axis here?
Here, this one, in blocks.
No, so, yeah.
You can see it here. Huh, okay, this is actually we use the gradient flow. Oh, sorry, I will explain that. This is the cutoff for the radius of the cluster decomposition. Yeah, I'll come to that. I'll just show that somehow within the earlier statistics. This is a lower statistics calculation, and we don't see much of a difference. But with the higher statistics, there's a slight difference. Yes.
So, I mean, those are topological susceptibilities from the two different definitions.
Yes.
They seem to agree.
They agree. Given the statistics, they agree. But I'll show you some of our new results.
The GG dual in this bottom plot, is it flowed already?
Yes. This is the float in certain T-5 or some value, typical values. Yes, sorry. Yeah, this is right. Oh, I'll explain that later. So now this comes to cluster decomposition principle with cluster decomposition error reduction. We know that from the cluster properties and so on, the operators, particularly color singlet ones, they have the property where exponentially fall as a distance. That's why when you do experiment, you don't have to worry anything on the moon. But there's also a power form in general. And these so one thought, well, this is the behavior of a boson propagator. One thought at that time, maybe since the operators fall off, you can at a certain distance you cut it off, and it won't change much of the result. Turn out when you cut off, if the signal falls off, the noise usually also fall off, so you're not really gaining anything. But there are exceptions. Let's look at the strangeness. Usually this is known that any of the disconnected insertions in the contacts, for example, we look at the glue operators, the alpha dual local ones, then is a disconnected insertion compared to in the hadrons and so on. But so let's consider a strangeness in the nucleon that involves a quark loop of the strangeness in the nucleon propagator. Okay, that's why it's called a disconnected. It's like a vacuum polarization, all right? And that is usually harder to calculate because when we do a connected insertions, you can use the translational properties. You can start at any particular space and time point and propagate. Then you get all the quark propagators in inverting of one column of a color spin, 12 columns, 12 color spin. But for the disconnected insertion, then you have to go from any point to any point and sum over through the momentum projection. That is not possible to do such a 10 million by 10 million matrix. You have to invert whole thing. So instead, people use the noise methods. Okay, and for the noise methods in our calculations for the loop, we have generated in general like 1,000 or 2,000 pairs of eigenvectors, low energy vectors, and you can see that in many cases the loop is dominated by low modes, low frequency modes, particularly the scalar and absolute scalar that with a 20, 30, or 100 moles, you can saturate that 20 to 99% or so. Scalar is not as good as superscalar, but probably will be saturated by 80%. The rest, you can use high modes to estimate it. Okay, once estimated. So let's look at this property here. You create a nucleon, for example, with 0 positions, and you end it here with certain position x. You do a projection to get a 0 momentum, and at certain time t. But in between that, you insert a strangeness loop. This is the strange loop here with the intermediate step tau here. Okay, so you can see when you then we can study. Usually, you take the r prime to sum of all the relative positions. For example, particularly relative to the sync position. Okay, well, when you usually do is you sum up all that 0 momentum strangeness loop that give a projection of 0 momentum. But you can look at that as function of the separation of distance of the operator to the sync positions. You can see this is the r, and once you go up, it's good. The number, the signal is going to saturate, but the errors start to blow up. Okay, particularly for the disconnect insertions. Another way of looking at it is that you look at the signal, which falls off this, but the variance or the error remains constant. Okay, so the reason turns out is the following. You can figure that out. Is that one can look at the variance disconnect insertion. You can look at the variance of this property. You have operator 1 or operator 2. The operator 1 will be the say a strange loop, and operator 2 will be the nucleon propagator. Okay, and you can see that because of the variance, you have O2, O2 dagger, O1, O1 dagger. These are scalars. You have a different summation of x and different coordinates and so on. But remember, this is O1, 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 2 are scalars. Therefore, there is a vacuum insertion that you can put in. So it's the vacuum here. When you have a vacuum insertion between two matrix elements, the fluctuation of these two are independent. Even though it started with 1 over v squared, then the vacuum fluctuation, each one is v, it cancels out the v squared, and this is independent of time. That's why you can see the variance or the error does not decay with respect to the distance. You expect usually for the connect insertions, the signal falls off, the error also falls off. So there's not much to gain. But here, you notice the error, the variance does not decay. And so this variance for the sum of everything is order 1. However, as we said, the signal should decay as exponentially, right? So there's no point in going over to a much longer integration. You don't need to go over a much longer distance. The signal is already falling off, right? So when you do keep on adding this thing, you're adding noise and no more signals. Here, signal is saturated. You're adding noise, no more signals. So one thing one can do and should do is cut it off with some way. Either you fit it or you cut it off with some smaller. You sum over an optimal volume Vs, and how to determine that, how to cut it off and how to fit it is another matter. You can use Akiake sort of information criteria to give you information as to how to get the systematic errors. That's another chapter. I won't get into it, but the idea is that you can cut it off and have a much smaller errors. Okay, and I'll see how to proceed. This is an example that I gave you earlier, the strangeness magnetic strangeness sigma terms. You can see, take a particular separation of the nucleon and sink and source. This is a longer separation. This is the one that you, as a function of the time separation of the current. Current sitting at 0, then you have negative and positive part. You can see that you have this form means that you have a excited state contamination somehow, which people usually fit the two state or three state to get rid of the excited state. But you can see this is the size of the error bars you get. On the other hand, if you cut it off, not a 27 is the maximum you get. If you cut off a 12, this is the size of error that you get. Okay, much smaller. And this is the larger the lattice, the better it's going, because it's, you know, your the cutoff radius or the physical or the correlation that you is actually fixed in physical scale. But when you go to larger volume, that becomes worse and worse. Therefore, I think this is essential to adopt some algorithm like this to see signal with the physical biomass at large volume. All right, and people have adopted such methods already. And for example, this is a cutoff, but you can see here, Ichibuki and so on have done a calculation where they use a sort of signal, a cylinder. This is to say a source and sink for the nucleon. They use a cylinder to cut off some radius here. And of course, Andrea also have done some direction truncation in the T directions. For us, what we do is this. For the alpha calculation, in other words, to calculate CP phase in the nuclear violating phase in the nucleon, it's a quark operator topological charge in the nucleon 2-point functions. So we just take a radius r, summing over this radius, and cut it off. Okay, these are topological charge, local topological charge here. This is sync positions. Now for the 4-point functions, usually electric dipole moment with a vector current, the connect insertion, and topological charge can be anywhere. We take a relative coordinates between the topological charge and the vector current. That usually it's a v squared operation. Sum over x position, sum over another relative coordinates r. That usually is a v squared operation. That's very expensive. We cannot afford it. What we can do is do a fast Fourier transform, okay, of these two coordinates, and then of course multiply back to get that is a v log v calculation, which is numerically it's okay, but it needs you need to save all these coordinates, and that's it's a storage problem if you need a large lattice. But as a separate issue numerically, but that can be done and has been done.
If you try placing the summation where the source of the same car instead of vector.
Oh, compared to here, instead of here, you put it here.
Yes.
We have not done that one. We have.
Our experience, at least in the time direction, was that the big chunk of the signal actually comes from the location of the Theta projector at the source of the same. So once you overlap the charge in the proper source of same location where the projector is,
yeah,
then you're essentially maximizing the signal, and the noise is all the rest of the duration function. So yeah, it would be interesting to see if you place your
over here
your charge and radius around either the source and the same. Depends where you put the projector.
Right, right. Actually, the rate now at this moment, yes, yes, we can try that. The thing is that we put the sink now as a smeared sink, not just point. It's a smear to make it a little bigger.
Oh, it doesn't matter.
No, I haven't tried that. Maybe that's another issue we could try. Maybe see whether that gives us better, because numerically it will be the same. It's not a difference. Yeah, that's true. That's true. That's true. And also depending how large the radius is. The radius at this moment, in our case, when the current's not too far here, it should cover that here. Okay, yeah, that's a good suggestion. I can look at that. Oh yeah, the projection of this one is this is the relative coordinates of this to the local current that we call off.
What is the current you're summing overall?
Current is summing of all. For all different tiles, and this is the not just you have a momentum projection on this one.
So the radius is relative to the particular.
R is relative to the topological charge and the particular point current at this point.
I guess what I'm confused is if you're summing the current location of the whole spatial volume
Yeah,
are like. the
will
rate
change. Yeah.
Are moving with.
Of course, it's all, as I said, it's relative coordinates. That's why we have to do the fast Fourier transform. Yeah, otherwise, yeah, you do the Fourier transform here. Yeah, but the current is all projected and for all the tiles and with a different momentum in order to extrapolate to zero. Okay, I should mention a little bit. Okay. So this is a case that we did earlier, a test of this for a relatively larger lattice than the ones we have, so 48 cube lattice with this lattice spacing, physical biomass. And you can see the R, well, this turns out a sign is different now. The alpha 1 fit space as a function of the cutoff, not a cutoff, but the accumulated. I should describe cutoff, but the accumulated results of a different R. It's accumulated. You can see this, usually you take this value at the very end, right? But if you consider, then this is basically flat within the region that you can see. If you take a value at 20, which you think is cut off, and then you get an error, which is about 1/3 what you can get. So basically you can gain probably a error in the factor 3. All right, let's go to a more studies which higher statistics that we have now. Then you can see for each configurations, we have these are now the gradient flow for the overlap for the configurations we have. Okay. Now you can see that different configurations, they're more or less flat, except a few cases, sometimes it's not completely flat. Okay, as a function of the flow time. And usually when take the cutoff as a square root of TF, and which is 0.6, 0.7, in our case is about 3.7 to 5 in this range.
Do they expect those to be integrated?
I'm sorry?
No.
Not exactly integers. For the overlap, what we do, of course, we use the local ones. If you consider 0 mode, it's integer. If you throw in the local, if some of the local integrated over, given enough statistic, it should be integer. But for us, we have estimate, but that's unbiased estimate. Okay.
Configurations have been produced with overlap.
No, configuration were produced by the domain wall. We took from RBC results, but their chiral symmetry is pretty good. Then we match the quark masses the same with the valence and the C, the unitary. But then you can have a partial quench. Overlap is easier to construct, 10 or 20 or 30 valence masses in one shot.
What's the definition of the chart you're using in this plot?
Oh, this is just the clovers and so on.
Or did you do?
G2, yes, right. This one is using the this because in the this is the flow with the GG2. Yeah. Now this is something which this is the average ones, some over 800 configurations now. Earlier, the one results show you probably 100 or 200 configurations. Now it's a higher statistic, and you can see the value with the cutoff, with a cut, not a cut, I should say not a cut, is accumulated results. Okay, you can see that the error bar in this one does not change very much for the topological susceptibility, which we don't understand why it does. But this is a small lattice, 20 to 4, so it probably takes longer. The physical radius for that to saturate is probably longer. But anyway, this is the you can get a number like that, 1.7. All right. However, if we take the gradient flow, right, different flow 1, flow 2, time once TF. Okay, but turn out there's a tendency for that to drift, even though the error bars are overlapping in some ways. We're not sure. We haven't talked to you. Maybe we should say whether you observe similar things like this, still drifting. So we actually when earlier results we're using the gradient flow. We thought that would be cheaper and so on. But turn out when we produce our configurations, we project the eigenvectors, we calculate local topological charge right away. So actually we're not really generate them separately. So we decided to use the overlap fermions to overlap topological charge. I think it's T, there's the T 1, 2, 3, 4, 5, and so the flow time intensity. Yes, sorry. It's supposed to be, as I said earlier, it should be 3 to 5 or 4 to 5 or so in this range.
But you kind of expect, right, to, I mean, start drifting down.
Why?
Because the more you, I mean, you smooth, I mean, your configurations, the more topological content you lose, right?
Yes, yes. I thought usually people say go to very far, then you would do. But
Region where, I mean, you should see a plateau.
We have a rather large range of flow times where the
project is come.
flow time independent.
Yeah, but at some point you start drifting down.
We didn't go there.
Yeah. But this is something which I like to consult other people to see. But now we have a earlier the statistics was not good. Now it's earlier, there's a tendency for that. We haven't tried the 7 and so
It's
on.
not that noisy, so you could actually
right.
try to do the simplest, just sum over the whole volume and just like the flow time independence.
Yeah.
Because the video you see it's very, very clean. It's not.
It's clean. You just worry about this sort of changing in flow time. We're not sure whether that. Yeah, maybe it's not something to worry about, but
No, it should flat. It should be constant. There should be a region in flow time where this is constant.
well, it is within error bar.
Well,
Yeah, it's within error bar, but there's some sort of tendency which we don't quite understand it.
took a bootstrap difference, you probably have a precise difference to it. Even though it looks like they overlap.
But they all correlated.
That's what I mean.
They're correlated.
You took the difference on the bootstrap, they probably would not be consistent with zero. It's correlated.
I should explain a little bit. We used to smear source and we put them in many places. In this 24 lattice, we put 8 of them. But for the larger lattice, we put 64 multi-grid points. Because of a low modes, we have to construct a new peon with the low modes in it, and the high modes will be approximated with the noise approximation. That you can gain a lot of statistics. With the 8, which basically the same calculation, one calculation with 8 sources, you can gain a error by a factor 2 or so. Okay, so that's what we'll be doing. And the sink, usually the last time we used the point sink earlier, which is okay, but the thing is when you look at the 4-point function as a function of the current positions, the thing is not symmetrical. So when you do the 2-state fit, it's a little more complicated because on the left-hand side and right-hand side, smear ones, you smear out the excited state. The point source have a lot more. Therefore, we switch over to smear to smear. Just to check that for the 2-point functions, but the point source, we're calculating of alpha 1, we use the 2-point function with the topological charge. You can see that there's no notable difference, just to make sure. Now, here's something which I'll explain. This is based on 2 different C parameters, 339, 576. Okay. Now you can see something, 2 things one can notice. One is that even the fixed, we have partial quenching with a different valence. Actually, one can do with the overlap fermion feature, you can do multi inversions with basically the same computer time. So in the past, we have do like masses, we do 20 to 30 masses in one shot, okay, partial quenched. But for this one, because analysis takes time, we only use 3 or 4 points. But you can see here, this is again a cutoff. You can see either here or some region here. You can see as you lower the C mass, the alpha negative ones becomes more and more negative, which is really surprising because you expect when the quark mass approaching 0, in a unitary setting, that alpha should go to 0. But this goes in the opposite direction. Okay, same is here. However, when you look at the following, when I take the same valence mass, but different C. This one, the purple ones, you can see is 389. The blue ones is 397. Basically, they're the same. But here it's minus 0.2, this is minus 0.45. So with the C mass, it does go to 0. Well, it gets smaller, but the valence has a different behavior, which will show up later in our calculation. Right.
In both plots, the heaviest mass is the smallest value.
It's just that when you take the
It goes to doing the C mass, but, oh, I see.
fix the C, and the valence gives the smaller mass give you a larger value, absolute value.
So the biomass in the legend is the valence biomass.
Right, in the legend is valence parameter. This is the C mass.
Oh, the unitary points doesn't change here. So the unitary point is essentially the red data on the right.
This one, the unitary point will be here, the blue, the red ones.
Let's say the red one, and here is also the red one, between the red one and the green one.
Right.
They
The
don't
red
seem to-
one is 0.02.
Yeah.
This one is red. Yeah, it goes down, all right. The red compared to red, right?
Yeah.
The red
So in
compared to
absolute
red,
value- in absolute
this-
value, alpha gets bigger.
this is 2 point something, right? This is 1 point something. So in a unitary point, it does. I'll show you the unitary
Okay.
point. The unitary point is no problem, but you disentangle them into the valence and C. It looks like the C goes down in the right direction, valence goes the opposite direction, which I'll show you the results really reflects that. So I just want to pre-warn you that from this thing, you already see something. From the alpha, you already, it's indication something is different for the valences. Now, here's the ratio of 4-point to 2-point function that we take. There are various ways for constructing this. They have different expressions for all give the same principle, the same result. Here we take one particular combination of that. It turns out it is alpha times F1 and alpha times F2. And this is the F3, the new F3, which has shown you F3 prime, the old ones, and 2 alpha 1, F2. Okay. Turn out all three of them are negative in our calculations. The F2 is negative because the neutron electric dipole moment, we know it's negative. And then the magnetic moment, the 2 alpha 1 is negative in our calculation, and the F3 is also negative. So therefore, this is positive, and this is negative. Now, depending on the cancellation, how large the cancellation is, so the net results can be positive and negative, depending on different people. Calculations may end up with a positive and negative value if you just look at this expression. However, this is neat in this particular combination. This can be summarized as F3. This is new F3 that you can extract, and this alpha 1 times GE. Okay, GE of the neutron, for example. And this is neat because when we do you need to do because it's F3 is somehow proportional to the momentum transfer, you have to take the 0 momentum transfer value. And the 0 momentum transfer value, you can see that GE is 0 for the neutron. Neutron charge is 0. Therefore, the expression, when you look at this, when you extrapolate to the 0 momentum transfer, it does not depend on alpha 1. So this is something which I thought is probably a neat way. When you do the calculation, you extrapolate, it should not depend on alpha 1. And then people have in the literature, there's some confusion. Some people got positive alpha 1, some people got negative alpha 1, depending their definition of a topological charge. Okay, so here is something that we did with a two-state fit. This is after, this is the first mass. In other words, for the, it's cut off here. So this is a lattice spacing, 0.114 Fermi, and 24 cube times 64 lattice domain wall. And we use overlap fermion on it with 339 MeV. Okay, this is the C biomass. We use the 3 of them. For this particular case, this is in principle, the most noisy case that we have. You can see that we take the cutoff at 5A, and For this particular lattice, you have a different separation as people usually do. Look at the current positions, starting 0, minus, plus 2. And the separation, you can see that the nucleon and source and sink separations is 6 lattice spacing. 10 is like 1.1 Fermi. But for this heavy pion mass or nucleon mass, for that matter, I think 10 is usually enough. Therefore, we have 3 curves, and you do extrapolation to state extrapolation, including the exponential terms from the separation. This is the gray band is what we got to fit. Okay, now let's look at the momentum extrapolations. And people have trouble looking at that. Turns out you can see that again is a plotted as cutoff of 4, 5, 6 all the way to 11 radius in the cedar cutoff. You can see that of course it changes somewhat, but they're all because basically after 4, 4, 5, after 5 or so they are more consistent. Okay, we have not done a completely analysis using the RTLK formula and so on. We take the value of 5, we think is okay. The value we have now, the preliminary results based on the 5 cutoff. You can see here 1 momentum, 2 momentum, 3 momentum, 4, and 5 momentum here. And that more or less like a linear, it's like a constant term. But anyways, we use the linear fit to get the results at 0 momentum transfer. Okay. Q squared the lattice units 2 pi L. The Q will be let me see. It's A is 0.114 Fermi. If the box size is 24, right? About 3 Fermi, 2.8 Fermi, 2.8 Fermi, 2 pi over L, 6 over 3 is about about 400 MeV.
Yeah, the first momentum is 450.
Q, the 3Q is about 400 MeV. The second one will be like the diagonal square root of that. Square root, this is one, this is Q squared now. Okay, earlier it's the 3Q is 400 and 600. Okay, square root. This is not very high. Well, depending, yeah. Right. Depending on what you, yeah, that's the lowest we can construct. The larger, now the next one we're trying to look is 48 cube lattice, 5.5 Fermi. Then the Q will be 250, 200. Yeah, that would be close. Of course, you have other things. But you can see it's rather flat. So we fit it linear. What the form factor, of course, just reflects the size of the object. That form factor, take a derivative of that, give you R squared. So this means this is very short range. The topological charge for this was very short range correlation with the nuclei. All right, so these are the things that we did with the 3 lattices. The C mass 339. This is like a unitary point. Each one's a unitary. Well, this one's a unitary point. Sorry, 339, 430, and 576. These 3 are we going to extrapolate. These are the 3 valence masses. Okay, this one basically matches that. This is a little lower, a little higher. We actually have a 4th one, which will include. I was promised the next week. The lattice conference will be coming down. And the valence here were 3 and also 4. And this one, the valence of only 3. Okay, but here's the results. Let me show you. Preliminary, very preliminary. This is a unitary point. You can see that this is the 300, 400, 500. Okay, this is the size of error that our final results are like. This one, unfortunately, we don't have. This is 800 configuration. This one, so far, we have only 100 configurations. And the next we will have coming down. And then we have a 5 momentum instead of 3. So the size of this error bar should be comparable to this one. Okay, but you can fit it. We fit it with the log term, and this is what we get. And so it's basically 1 sigma. It's really not much of an improvement. 1 sigma
How many sources do you use?
For this, it's hard. We have a grid, right? 8 sources, which is probably a square root of 2 times the deduction error, and we use coherent source with a 2 at the same time. Of course, we can also mark it long. We haven't done that yet.
I mean, this data.
Question.
Are like 10 sigma.
Oh yeah, oh yeah. Oh, yeah. Probably more than 10 sigma. In other words, all the 3, I would expect all 3 will be eventually 10 sigma with there. Wait a minute, wait for next week, hopefully. Now here is now with the partial quenching. As you see here, let's look at this case. Take the blue ones, which is the lowest C mass, 300. You can see it goes up in this direction. The valence, as the valence masses goes up in this direction. As I warned you before, the alpha goes in the opposite direction. And this one is also, and this one, of course, the error bar is large, will come down. We have all the data, it's just a matter of manpower to analyze it. Okay, so what happens is the following. We found that when we first look at that, well, something is wrong because the error bar was larger earlier. Well, something's wrong. Never seen anyone with a chiral behavior with the valence in C goes in the opposite direction. There's no other quantity that we know of that we have encountered. Here's probably the first example. Turn out there is a calculation of partial quenching where you can see that there is explicitly C valence mass difference. Okay, and turn out the coefficient is such that is negative or something. Okay, so that can, then including this term, one can fit it with. Now, one thing that we did fit, I should mention, particularly, we know exactly this point. Well, when we do the fit, we include this point, which is 0. In other words, we put the functional forms and pi squared times that. Okay, we know this term is 0. And then that we fitted this form, we simulate like that. We fit 3 coefficients. That's how we got this number here. But the data we have at this point is 4 sigma at this point. But hopefully, the results will be better when we have the other one coming there.
Yeah, it turns out to be positive.
I'm sorry?
It turns out to be positive.
Which one's positive? Yeah.
Median.
Yes, this is positive. The thing is, I should mention, as I said, the alpha 1 times F2 is slightly larger than F3, the old F3. That makes it, let's go back. As I said, depending on the alpha, it can turn out positive and negative because all these 3 terms are negative. So this is positive, this is negative. Turned out in our calculations, this is slightly overcome the other ones. The other people probably have the other way around. The thing is that perhaps the alpha 1 that we calculate needs to be larger. I don't know. One needs to have a more detailed study. But in this case, we are slightly larger. So it's probably turned out to be positive. Yeah, we've been struggling with the sign too for quite a while. For quite a while. Yeah. No one understands that's how it happens. Physical point is numerically challenging, still challenging, given this, especially we have not gone into the physical power mass, the C power mass yet. That is a large volume. The hopeful thing is that you have a cluster decomposition. It does not get worse when you get a volume larger. You cut it off early, not earlier, but physically cut off the physical side, not the volume side. Okay, hopefully that will help. And chiral symmetry is of special importance in theory calculations. We know in this case you have an anchor. In other words, you know it's 0 at 0 quark masses for the overlap fermion. That's a big anchor to show that you have the results. Okay, and the cluster decomposition error reduction (CDER) will be essential for large lattices for all the disconnect insertions, the glue operators, the quark loops calculations. We have been using this. This seems to be very helpful, very essential, especially for large lattices. And more statistics are coming. Actually, we have them partial quench biomass will be added have a more reliable car extrapolations. Hopefully we'll have some results very soon, hopefully next week. Yes, the largest quark mass is 8 times the statistics and 5 momentum transfers instead of 3. And that will bring down the statistics and so on. And it should be comparable, hopefully comparable to this. And of course, the future will be larger lattices, which are prepared to do. Physical biomass will be next target. There will be a challenge still. Yeah. Okay, that should be all for my talk.
Okay, thank you very much, Keh-Fei. Very exciting results. Comments, questions? At home?
Yeah, so thank you for the talk. And do you have some estimate on the computational request to do the simulations at the physical point? So you have some rough idea how much you would need on a pre-exascale computer, so to speak. So is it realistic?
Time,
yeah.
We have, I think we have enough computer time.
Okay.
Like closer to like 1 million node hours at NERSC or at an SFG. What worries us is the storage. The thing is,
Interesting.
You have to put all, you have to go to the fast Fourier transform, you have to store all the loop in the coordinates and also the 3-point function in coordinates. And the 24 lattice already requested extra disk space to analyze that. They allow us 48 will be more of it. It's not a computer time. I think computer time we can handle. It's the storage that in many cases nowadays people are, of course they want to, every computer center they want to be the first in the 500 listing in the world class. They're looking for speed, but this space, tape space and all that is the secondary.
No, that's right, because we start hearing indeed the future calculations will be memory limited rather than, but then it's very interesting to have very specific important examples.
Yeah, hopefully there will be some centers that do thinking of that large data center to have fast access to data. That seems to be next computer center tower.
Hi, thank you for the nice talk. So I have a question about the plots you showed for the topological susceptibility.
Yeah.
So I'm not sure I understood how you computed that. So you have overlap fermions, so you compute the topological charge but count in 0 modes, right?
Yes. That's one way to do it. Yes, we have the 0 modes. We calculate for each configuration. We just take a Q squared. That would be it. That's one way. But we also have, since we need a local topological charge, we calculate the dxx, the overlap xx, the diagonal terms. We use the low modes to saturate for the eigenmode expansions. For the low modes, we use the exact ones. High mode, we use the noise estimate. 256 noises. That give you something like, for each configuration, it's not exactly integer as in from the 0 modes. It's about within 5 to 10% fluctuations, but it's an estimated error, but not unbiased errors. So when we do the local ones and you sum that up, it's not exactly the same as the
okay, so you computed the density and then you integrate it.
Yeah, because we need the local topological charge. We need to calculate the local charge for this.
Okay. And you do these calculations for several values of the gradient flow time?
Well, sorry, I'm sorry.
That's the separate calculation.
That's separate. Okay.
They fill the gauge definition of the chart.
Okay. Thank you.
Yeah, my question. Which definition of the
I didn't
charge?
understand it.
Maybe Keh-Fei can clarify.
You have the definition of the charge, one coming from the overlap density action and one coming from the Coulomb definition. And you integrate over this sphere, the overlap definition, and then you flow the gauge one.
That's right, for the topological charge. Yes, right. We take the configurations and float time. So the other one is overlap definition. Then there's no flow. Okay, overlap, you don't need a flow. For the other definition, you need to, yeah, it's either flow or overlap.
So usually when you flow, I mean, you need to keep, I mean, a physical scale fixed, right?
If you do the continuum limit, yes.
Continuum limit, yeah. But I think with the
You-
overlap, we don't need continuum limit. The topological charge is no multiplicative minimization is integer.
Mhm.
So I should mention the topological charge is no multiplicative minimization. The vector current is overlap. We use the local current. If you use the non-local current, there's no normalization. Again,
Okay,
we use the ZA and ZV. It's actually normalization, not renormalization. It doesn't diverge. It's coming from the either the say the nuclear sort charge, or because the ZV is same as ZA in the overlap fermion with the power fermion. So you can look at the PCAC relation, get a very precise ZA, you use that as ZV. Turned out to be the same as
okay,
a calculation of the charge, which requires 3-point function calculation.
okay. But you also, when you do that, like the chiral fit, I mean, you have like for several pion masses, I mean, you calculate topological susceptibility, or I mean, a quantity which depends on topological.
Oh, yeah.
I
you can
mean,
do that.
also there you need to keep like a scale fixed, but the scale won't, I mean, depend strongly on the pion.
Depends due to the port mass dependence of the lattice spacing.
Yeah,
Yeah, I thought some of that, Juicy has done quite a bit of overlap and use, I can just using the zero mode, right? Using
yeah,
zero
okay,
mode.
fine.
And study that as function of the quark masses. So see that you should go to zero, it's the quark mass, right? There's quark
Yes.
mass dependence on topological charge. So the
Right.
conversion is the-
Actually, I wanted to ask you, what definition of the charge you use for the plot of the EM you've shown? The one with the overlap fermions or the one from the gluon definition?
we used the overlap now.
So
Earlier results, we used the
So this plot you show with the EM, the charge is calculated with the overlap.
with overlap. As I said, we look at the flow time. We're not quite 100% happy with that, so we just switch over to the overlap, which is the same calculation. You know, it's very
Can I
easy. It's just in the analysis.
Oh, there
stage.
is a question.
No, I don't know, I'm asking if you want
No.
to ask the same question.
Yeah, one more thing. I find very interesting that the fact that the topological susceptibilities calculated with the
Overlap.
fermion, yeah, the overlap fermions and the gluonic definition are, I mean, consistent. I mean, for instance, when we do spectral projectors, I mean, the topological susceptibility,
You have to agree with the continuum limit.
yeah, they will have to agree at the continuum limit.
Yeah, it's slightly different depending on, you can see that's the
Not-
137 here. There's a slight difference. Yeah.
I was
So I don't
referring
know.
to, I mean, a plot you showed before. I mean, when you go back.
Oh, that one's a low statistics.
Okay,
So you cannot tell the difference. Now, as I said, without this is like 200 configuration, 100. Now the 800 configurations, we start to see a difference.
okay.
So that got us a little concerned. You know, just to be safe, we switch over to overlap. I don't think it probably won't make much of a difference in the end, but you know, we're just not sure. We cannot, you know, if one has time, we can analyze both. It should not be hard to analyze both of them.
Have you checked the mass dependence of the susceptibility and ensembles you have?
We should have results, but I haven't seen it yet. It should be. First, yeah.
Okay, thanks.
Are there questions at home? On Zoom?
Not from me, thanks though.
Okay, so we reconvene here at 2:30, all right? Sorry, guys.
2:30.
Is it 2:30?